السلام عليكم ورحمة الله وبركاته. الحمد لله رب العالمين، والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Inshallah, we are going to have a series of videos in which we will discuss and explain cardiovascular physiology. In these two lectures, we will be describing the basic concepts in cardiovascular physiology, and these concepts will be described and explained in details in the subsequent lectures in the course. These are the learning outcomes of these two lectures, and the learning outcomes are clearly defined statements which reflect and describe what is expected from you as a student after reviewing the PowerPoint presentation and the lecture notes and the associated material. And we will go through these learning outcomes again during the class time. These are the learning resources for these two lectures and for the cardiovascular physiology in general. And I would recommend that every one of you would have the Linda Costanzo Physiology 5th edition. This is a good book with simple English language and with good physiological explanation. So to start with, as you all know, the cardiovascular system is one of the major and important body systems. It consists of the heart, which functions as the central pump of the cardiovascular system, and the blood vessels, and the blood which circulates along the blood vessels. And as you can see here, the cardiovascular system, it is a closed system in which blood circulates, and because of that, the cardiovascular system is also known as the circulatory system, or simply the circulation. Again, in this slide, we have the major components of the cardiovascular system: the heart and the blood vessels. And inside the blood vessels, blood circulates. In the blood vessels, we have arteries, we have capillaries, and we have veins. From this diagram, we can differentiate between the arteries and the veins of corresponding side, that the arteries are thicker walled than veins of corresponding size, and the arteries, they have high pressure than the veins, and that's why the arteries serve as pressure reservoirs. Another very important difference between the arteries and the veins, as you can see in this figure, that the veins can accommodate large volume of blood than the arteries, and because of that, functionally, the veins can be considered as volume reservoirs. And what makes the veins accommodate larger volume of blood than the arteries is because they have high compliance. The compliance is the ability for distensibility. So the veins are more distensible than the arteries. They can be distended and accommodate larger volume of blood than the arteries. Remember, again, these two lectures are introductory lectures, and all these concepts will be described and discussed in details in the subsequent lectures. These are the blood vessels again. So we have the arteries, we have the capillaries, and we have the veins. And from the structure point of view, all of the blood vessels have a common histological structure, and the wall is composed of 3 layers. We have the innermost layer is known as the tunica intima, the middle layer is known as the tunica media, and the outermost layer is known as the tunica adventitia, and this will be described and explained to you in the histology lectures. The wall of the blood capillaries is composed of only 1 layer. It is a single layer of endothelial cells resting on a basement membrane, because it is at the level of the blood capillaries that we have the exchange of the respiratory gases and nutrients between the plasma inside the blood capillaries and the interstitial fluid. Again, here we have the blood vessels. So we have the arteries. These are all arteries. Then we have the capillaries and we have the veins. The arteries are further subclassified into elastic arteries or big arteries or large arteries. And these large arteries or the elastic arteries, they are so called elastic because they have a large proportion of elastic fibers in the middle layer, in the tunica media, and because of that they can be expanded and accommodate the blood which is ejected by the heart. The major elastic arteries in the body are the aorta, which is the biggest artery in the body, which arises from the left ventricle, and the pulmonary trunk, which arises from the right ventricle. These two are elastic arteries, so they can accommodate the blood which is ejected by the left ventricle into the aorta, and the blood which is ejected by the right ventricle into the pulmonary trunk. Then we have the medium-sized arteries or the muscular arteries. They have large proportion of smooth muscle cells in the tunica media, and that's why they cannot be expanded as the elastic arteries. Then we have the smaller arteries are known as the arterioles. And the arterioles, the wall again, they have larger proportion of smooth muscle cells in the tunica media. And we can consider the arterioles as the doors to the capillaries. So these doors can be opened or can be closed, and based on the degree of opening or closure of the arterioles, this would determine the amount of the blood which flows through the capillaries. Then we have the veins, and in the veins we have the venules. The venules are the smallest veins. They collect blood from the capillaries. Then the venules, they join together to form the medium-sized veins. Then the medium-sized veins, they join together to form the large veins. So the arteries, they conduct or they transmit blood away from the heart, whereas the veins, they transmit blood towards the heart. So the arteries, their function is to distribute the blood, whereas the veins, their major function is to collect blood and return it to the heart. The biggest veins or the largest veins in the body are the superior vena cava and the inferior vena cava, which open into the right atrium. And we also have here 4 pulmonary veins which open into the left atrium. So having finished with the major components of the cardiovascular system, the heart and the blood vessels, let's very briefly describe what are the major functions of the cardiovascular system. One important function is the delivery of oxygen, glucose and other nutrients to the active tissues. And this is the function of the heart and the arteries, because it is the arteries which distribute the blood ejected by the heart to the active tissues. Then the tissues would use the glucose and oxygen for the metabolism, and while they utilize the glucose and oxygen for metabolism, metabolic waste products are produced, and these metabolic waste products need to be removed from the body. So another function is the removal of carbon dioxide, lactate, and other metabolic waste products from the active tissues. And this is the function of the veins, not the arteries, because the veins, they collect blood from the capillaries and return it to the heart. Very importantly is the adjustment of the oxygen and nutrient supply in different physiological states. So not only the arteries supply the active tissues with oxygen and glucose and other nutrients, but also there is a regulation of the amount of the blood which should flow through the tissue, and hence the amount of oxygen and nutrients. And this depends on the physiological state of the tissue. For example, during exercise, more blood would go to the skeletal muscles, which means that the doors of the capillaries of the skeletal muscles, the arterioles in the skeletal muscles, would be more dilated, more open. So more blood would flow to the skeletal muscles. Another important function is the transport of metabolites and other substances from storage sites, transport of hormones from the endocrine glands, antibodies, from the immune system, and other substances to the site of action. Defense is another important function by the white blood cells in the blood, and also the cardiovascular system plays an important role in thermoregulation, and this was described and explained to you in the lectures on homeostasis. So now let's focus on the heart as the central pump of the cardiovascular system. The heart is a muscular organ composed of 4 chambers: 2 atria, the right atrium and the left atrium, and 2 ventricles, the right ventricle and the left ventricle. The right ventricle and the left ventricle are the main pumps of the heart. The right ventricle is known as the right pump of the heart, and the left ventricle is the left pump of the heart. Arising from the left ventricle is the biggest artery in the body, which is an elastic artery. This is the aorta. So when the left ventricle contracts, it ejects blood into the aorta. And the aorta, being an elastic artery, it expands and accommodates the blood ejected by the left ventricle. The right ventricle is the right pump, and arising from the right ventricle is the pulmonary trunk, which is again a large and elastic artery. The atria, the right atrium and the left atrium, they are not pumps. Their function is to receive blood. They are receptacles of blood. So the right atrium receives blood from the superior vena cava and inferior vena cava. And the left atrium receives blood from the pulmonary veins. The blood which is received by the right atrium from the superior vena cava and inferior vena cava, this blood comes from the tissues, so it contains carbon dioxide and it is deoxygenated blood. Whereas the blood which is received by the left atrium by the pulmonary trunks, this blood comes from the lungs, so it is oxygenated blood. The contraction of a cardiac chamber is known as systole, while the relaxation of a cardiac chamber is known as diastole. So when the left ventricle and the right ventricle contract, when they are in systole, they pump blood into the aorta from the left ventricle and into the pulmonary trunk. While when the right ventricle and the left ventricle are in diastole, while they are in relaxation, they receive blood. The right ventricle receives blood from the right atrium, and the left ventricle receives blood from the left atrium. So the function of systole is mostly the ejection of blood, while the function of the diastole is the filling of the heart with blood. The contraction and the relaxation of all the 4 cardiac chambers is what we call the heartbeat or the cardiac cycle. And remember, systole is as important as diastole, and diastole is as important as systole. Both are important because during diastole the heart is filled with blood, and during systole the heart pumps blood. In the heart we have valves. So we have valves between the atria and the ventricles. These valves are known as atrioventricular valves. We have the tricuspid valve between the right atrium and the right ventricle. And we have the mitral or the bicuspid valve between the left atrium and the left ventricle. The tricuspid valve is called tricuspid because it has 3 cusps. 3 ضرف للvalve. And the bicuspid valve is composed of only 2 cusps. Now, what are the functions of these 2 valves? They allow the blood to flow from the atria into the ventricles during diastole. And when the right ventricle and the left ventricle begin to contract, these valves are closed and they prevent the backflow of the blood from the right ventricle into the right atrium and from the left ventricle into the left atrium. So these valves, the tricuspid valve and the mitral or bicuspid valve, they ensure unidirectional flow of the blood from the atria into the ventricles, and they prevent the backflow of the blood from the ventricles into the atria. Additionally, we have a valve between the left ventricle and the aorta. This is known as the aortic valve. And a valve between the right ventricle and the pulmonary trunk, this is known as the pulmonary valve. The aortic valve and the pulmonary valve, they are known as the semilunar valves, الصمامات الهلالية. Similarly, these valves, they ensure unidirectional flow of the blood. So they allow the blood to flow from the left ventricle into the aorta during systole, and also from the right ventricle into the pulmonary trunk during the systole of the right ventricle. And when the left ventricle and the right ventricle finish with systole and they begin to relax in diastole, these 2 valves, the aortic valve and the pulmonary valve, close in order to prevent backflow of the blood from the aorta into the ventricle and from the pulmonary trunk into the right ventricle. So we have described briefly the function of the heart as the central pump of the cardiovascular system, and now let's describe some important definitions which explain the heart function. So systole, we explained what is meant by systole, what's meant by diastole, and what's meant by the heartbeat. So the heartbeat is the systole and diastole of all the cardiac chambers, which is also known as the cardiac cycle. At rest, the heart of a normal adult male beats automatically and regularly at a rate of approximately 70 beats per minute. So obviously this heart rate increases during exercise, and the maximum heart rate during exercise in a normal adult male and female is 200 beats per minute. The normal range of the resting heart rate is between 60 and 100 beats per minute. 70, this is the average, but it can range from 60 to 100 beats per minute at rest. If the heart rate is faster than 100 beats per minute, this is known as tachycardia, and when the heart rate is slower than 60 beats per minute, this is what we call bradycardia. As we get older, there is no change in the resting heart rate, but the maximum heart rate during exercise decreases from 200 to 160 beats per minute. So the rare effects of age on the heart rate. Other important definitions which describe the heart function: end diastolic volume. These are the ventricular volumes. We are now describing some important ventricular volumes. and the first important ventricular volume is the end diastolic volume, ADV. This is the volume of blood in the left ventricle or in the right ventricle at the end of the diastole. So when the left ventricle is fully filled with blood, and when the right ventricle is fully filled with blood, the volume which the left ventricle contains and the volume of the right ventricle contains, we call it the end diastolic volume. How much is this volume? 135 milliliters of oxygenated blood, red blood in the left ventricle, and deoxygenated blood, which is blue blood in the right ventricle. So the left ventricle would contain 135 milliliters, and the right ventricle would contain equal amount, 135 milliliters. When the left ventricle contracts and ejects blood into the aorta, it doesn't eject all the 135 milliliters. There is still volume remains in the left ventricle, and volume of the blood remains in the right ventricle. This volume is what is known as the end systolic volume, ESV. So this is the volume of the blood which remains in the left ventricle and which remains in the right ventricle when they finish with systole, at the end of systole. And it is approximately 65 milliliters in the left ventricle and 65 milliliters in the right ventricle. So, having said so, how much blood the left ventricle would eject and how much blood would the right ventricle would eject in one heartbeat or in one cardiac cycle or in one stroke, this is what we call stroke volume, SV. So this is the volume of the blood which the left ventricle ejects into the aorta and the right ventricle ejects into the pulmonary trunk per beat. Obviously, it is equal to the difference between how much blood was in the left ventricle and right ventricle before ejection and how much blood remains by the end of systole. So it is equivalent to the difference between the end diastolic volume and the end systolic volume. 135 minus 65, it is about 70 milliliters of blood. Now, the left ventricle and the right ventricle have finished with systole, and each ventricle has ejected 70 milliliters of blood. And they began with their diastole, and they need to be filled with exactly the same volume which they have ejected into the left ventricle and into the aorta by the left ventricle and into the pulmonary trunk by the right ventricle. And this volume is what is known as diastolic filling volume, because the filling occurs during diastole, diastolic filling volume. So this is the volume of blood which flows from the right atrium into the right ventricle and from the left atrium into the left ventricle during diastole, and it is equal to 70 milliliters of blood. Some more important definitions which describe the cardiac function is the cardiac output, CO. The cardiac output, this is the blood flow generated by the left ventricle into the aorta and by the right ventricle into the pulmonary trunk per minute. So it is the blood pumped by each ventricle per minute. The stroke volume, this is the volume of the blood pumped by each ventricle in each one single beat. Cardiac output, this is the volume pumped by each ventricle in each minute. So the cardiac output is then equal to the volume of the blood pumped by one ventricle per beat multiplied by the number of beats per minute. So cardiac output Q dot, كلمة dot means per minute لأنه rate معدل, is equivalent then to the stroke volume multiplied by the heart rate. Stroke volume at rest, we have all agreed that it is 70 milliliters ejected by the left ventricle into the aorta and the right ventricle into the pulmonary trunk, multiplied by the heart rate, and the heart rate at rest is 70 beats. So if we multiply 70 by 70 يطلع لي 4900 ملي لتر في كل دقيقة. يعني تقريبا 5000 ملي لتر في كل دقيقة، وكل 1000 لتر 1 liter, so it is approximately 5 liters of blood in 1 minute. So this is the ejection of the blood in 1 minute. Venous return is another important definition which describes the cardiac function. The term venous return, VR, refers to the volume of the blood which returns to the heart in 1 minute. So this is the volume which enters the right atrium in 1 minute, which is exactly equal to the volume which enters the left atrium in 1 minute. We have all agreed that the cardiac output at rest is about 5 to 5.5 liters per minute. This is equal to the heart rate multiplied the stroke volume. So this is the volume which is ejected in 1 minute, which is equal to the volume which is received, which is filled, which is the heart filled with in 1 minute. So venous return is also equal to 5 to 5.5 liters in 1 minute at rest. So this is the flow rate into the heart, while the cardiac output, this is the flow rate out of the heart. So the venous return would be then equal to heart rate multiplied by the diastolic filling volume. So now, having said so, it is obvious that the heart as a pump, as the central pump of the cardiovascular system, has two major functions. The generation of outflow with pressure from the heart and the filling of the heart. So the human heart functions as the central pump in the closed circuit of the cardiovascular system. Thus, the cardiac output of the left ventricle, which is the amount of the blood ejected by the left ventricle into the water in 1 minute, this cardiac output of the left ventricle goes to the tissues. The tissues take oxygen and nutrients, then carbon dioxide retains. This is exactly equal to the volume of the blood which returns to the right atrium in 1 minute. This is venous return now. So this is left-sided cardiac output is equal to the right-sided venous return. Similarly, the cardiac output from the right ventricle into the pulmonary trunk goes to the lungs. So this is cardiac output, which is 5 to 5.5 liters per minute at rest. This goes to the lung, and in the lung, blood is recharged with oxygen. So then now oxygenated blood returns to the left atrium. So now this is venous return to the left atrium. So right-sided cardiac output is equal to left-sided venous return, and left-sided cardiac output is equal to the right-sided venous return. Again, we are still describing the function of the heart as the central pump of the cardiovascular system. And let's describe what are the requirements for effective pumping of the blood by the left ventricle into the aorta and the right ventricle into the pulmonary trunk. So for effective pumping, the heart must be functioning properly in 5 basic respects. The first respect, or the first aspect, the contractions of the individual cardiac muscle cells, which we call myocytes, must occur at regular intervals. Contraction, then followed by relaxation. Contraction, followed by relaxation. And all the cardiac muscle cells, which we call them myocytes, their contraction should be synchronized, yani at the same time. They should contract at the same time. So they should not be arrhythmic. Arrhythmic is when the individual cardiac muscle cells, they contract not at the same time. The valves must be open fully. They should not be stenotic. Stenosis means narrowing of the valves. and the valves must not leak. The valves should not be insufficient, ما عندهاش الكفاءة. And we should not have regurgitation. Regurgitation هو ارتجاع الدم. The ventricles, the ventricular contraction must be forceful. بقوة, لأن the ventricles, these are the main pumps of the cardiovascular system. And equally important is that the ventricles must be filled adequately with blood during diastole. So the ventricular contraction must be forceful during systole, and the ventricles must be filled adequately during diastole. Okay, so here we have two important questions for you to think about the answer. Specify 5 different mechanisms which can lead to ineffective cardiac pumping. So what are these 5 mechanisms which can lead to ineffective pumping of the heart? Is when the individual cardiac muscle cells do not contract at the same time, and when the valves are stenotic, when the valves are insufficient, when there isn't enough force during systole, or when there isn't enough filling during diastole. See, so these are the 5 main mechanisms which would lead to ineffective pumping of the heart. Another question is, think of 5 possible cardiac diseases which may precipitate ineffective cardiac pumping. What are these 5 diseases? Then we will go through these 2 questions during the class time. So now let's define cardiac function in modern physiological terms and explanation. As we mentioned in the previous slides, the major functions of the heart as the central pump of the cardiovascular system is to provide outflow from the left ventricle into the aorta and outflow from the right ventricle into the pulmonary trunk. And then to get filled, the left ventricle is to get filled from the left atrium, and the left ventricle is to get filled from the right atrium. So the blood which is ejected, the outflow of the blood, the cardiac output of the left ventricle, it goes from the left ventricle into the aorta, then through the branches of the aorta, going to the tissues of all systems of the body, to the capillaries of all systems of the body, to provide the tissues of all systems of the body with oxygen and nutrients. Then the tissues of the systems of the body utilize the oxygen and the nutrients, the glucose and nutrients for their metabolism. Carbon dioxide and other metabolic waste products are produced, so these need to return to the heart, to the right atrium. So then the deoxygenated blood flows from the right atrium to the right ventricle. The right ventricle produces outflow into the pulmonary trunk, so that blood goes to the lung to get reoxygenated, and the reoxygenated blood goes to the left atrium, then it flows to the left ventricle to be pumped again to the tissues of all systems of the body. So inside the cardiovascular system, blood flows through 2 major circulation, through 2 main circulations. We call them the systemic circulation and the pulmonary circulation. The systemic circulation begins at the left ventricle, where oxygenated blood is ejected into the aorta. Blood goes through the aorta, systemic capillaries, systemic veins, then deoxygenated blood returns to the right atrium. And it is at the right atrium where the systemic circulation ends. Then we have another circulation. We call it the pulmonary circulation. This begins in the right ventricle, where deoxygenated blood is ejected into the pulmonary trunk, goes through the lungs for reoxygenation, then returns to the left atrium where the pulmonary circulation ends. The systemic circulation is so-called systemic circulation because the oxygenated blood goes through all systems of the body, and deoxygenated blood is collected from all systems of the body. Pulmonary circulation is so called pulmonary circulation because the deoxygenated blood goes through the lungs for reoxygenation and then returns from the lung after reoxygenation to the left atrium. So here again, this diagram shows these two circulations. And these two circulations, each circulation has got a pump. The pump of the systemic circulation is the left ventricle. So this is known as the left pump, whereas the pump of the pulmonary circulation is the right ventricle, is the right pump. So the heart functions as two pumps. Now, a very important question to you guys is, these two circulations, are they connected in series, which means that one circulation ends and the other one begins, or are they connected in parallel? So remember, so this is now a simplification of the systemic and pulmonary circulation. From this diagram, you may be confused, and you may say that these two circulations are connected in parallel. However, in reality, these two circulations are connected in series, because look, this is one circulation from the left ventricle into the aorta, into the capillaries, then veins, then it ends here, the systemic circulation. Then the other circulation begins here. So one ends and the other one begins. It goes through the lungs, then it ends, this is pulmonary circulation, ends in the left atrium. Then the systemic circulation begins. So these two circulations are in series. So one circulation ends and the other one begins, because the reason why Allah subhanahu wa ta'ala has made these two circulation arranged into series, because now this oxygenated blood has to go through all systems of the body, then it returns to the right atrium, to the right ventricle. Then the same volume of blood has to go through the pulmonary circulation for recharging the blood with oxygen. So now this is the left ventricle. This is where the systemic circulation begins. This is the aortic valve. So the left ventricle ejects blood into the aorta through the aortic valve during systole, and the aorta being an elastic artery, so it expands and it accommodates the stock volume ejected by the left ventricle. Then this blood, it goes through the branches of the aorta, through the medium-sized arteries, then through the arterioles. These are the arterioles. And remember, I told you that the arterioles are the doors to the capillaries. So they determine the diameter of the arterioles, determine how much blood flows through the capillaries. Then we have the capillaries, where we have the exchange of oxygen and materials with the interstitial fluid, then with the cells. Then we have here the venules, then the veins. Then the biggest two veins in the body are the superior vena cava and inferior vena cava, the veni cava. Veni cava جمع superior vena cava or inferior vena cava. Here we have the right atrium. So it is here where the systemic circulation ends. Then blood flows from the right atrium into the right ventricle through the tricuspid valve, then from the right ventricle into the pulmonary trunk and pulmonary artery through the pulmonary valve, then through the pulmonary capillaries for reoxygenation, and oxygenated blood returns to the left atrium by 4 pulmonary veins. In this diagram, it is shown only 2 for simplicity, but in reality, there are 4 pulmonary veins, and it is here where the pulmonary circulation ends. So these two circulations are connected in series. We are still discussing the function of the heart as the central pump of the cardiovascular system, and we mentioned that in reality there are two pumps, the left ventricle, the left-sided pump, and the right ventricle, which is the right-sided pump. Now, why do we need to have the heart in the cardiovascular system? Now, in order for the blood to move along the arteries, we need to have pressure in the arteries, because it is the pressure which drives blood along the arteries after it has left the heart. So the left ventricle, it is true that it generates outflow, cardiac output of oxygenated blood into the aorta, but it generates this cardiac output with pressure, so that this pressure pushes the blood along the systemic arteries to go to the tissues of the systems of the body. Similarly, the right-sided pump, the right ventricle, ejects the cardiac output with pressure into the pulmonary artery, so that now this deoxygenated blood is pushed along the pulmonary arteries through the lungs for reoxygenation. So then the left-sided pump, the left ventricle, and the right-sided pump, the right ventricle, they generate two important things. They generate flow of the blood, flow, and they also generate pressure, because the generation of flow is not enough. They also should generate pressure to push the flow of the blood along the arteries after the blood has left the heart. Now, the important question is, why should the left ventricle generate pressure? Wouldn't it be enough for the left ventricle to generate only flow? Similarly, why the right ventricle should generate pressure? Wouldn't it be enough for the right ventricle to generate only flow into the pulmonary trunk? No, it is not enough to generate flow only. Why? Because as the blood flows through the systemic and pulmonary circulations, friction, احتكاك, develops between the moving fluid, between the blood and the stationary walls of the blood vessel, because the walls are stationary, they do not move. So as blood moves through the systemic circulation and through the pulmonary circulation, في مقاومة, there is resistance, there is friction of the movement of the blood through the systemic and pulmonary circulation. Thus, the vessels which we have in the systemic circulation and the vessels which we have in the pulmonary circulation, they tend to resist the movement of the blood through them. Such resistance is known as the vascular resistance. It is the resistance of the blood vessels to the flow of the blood through them. The resistance to the flow of the blood through the systemic circulation is known as the systemic vascular resistance, and the resistance to the flow of the blood through the pulmonary circulation is referred to as the pulmonary vascular resistance. Now, a question for you guys. Do you think now the resistance which the blood meets as it flows through the systemic circulation, is it equivalent to the resistance which the blood meets as it flows through the pulmonary circulation? Are these two resistances equal? Definitely they are not equal, because in the systemic circulation, blood has to move a long journey, because it goes to all systems of the body. كل السيستمز، بيروح للسكن، بيروح للمصل، بيروح للبون، بيروح للايز، بيروح للستومك، للdigestive tract، للliver, all systems of the body. Whereas when the blood flows to pulmonary circulation, it only flows through the lungs. So obviously the systemic vascular resistance is much higher than the pulmonary vascular resistance. In fact, the ratio of the pulmonary to systemic vascular resistance is approximately 1 to 6. يعني resistance في systemic circulation is 6 times higher than the resistance in the pulmonary circulation. It is because the vascular resistance, because there is vascular resistance in the flow, that we need to have the heart in the vascular system. Because we need to have pressure to overcome the resistance. يتغلب على الresistance. Okay, so again, we are still describing the function of the heart in modern physiological terms. And let's describe a very important law in physics, which is Newton's first law of motion. Newton's first law of motion states that an object at rest tends to stay at rest, and an object in motion tends to stay in motion, and with the same speed and in the same direction, unless acted upon by an external force. يعني لو في object at rest هيفضل at rest إلا لو أنا pushed this object with a force. ولو كان الأوبجكت ده ماشي بسرعة وباتجاه معين سيظل يسير بنفس السرعة وفي نفس الاتجاه إلا لو في external force acted upon this object. Do we have an object in the cardiovascular system? Yes. So what is the object which we have in the cardiovascular system? Our object is the blood. Now let's apply Newton's first law of motion to the cardiovascular system. If we apply Newton's first law of motion to the cardiovascular system, we can conclude that blood cannot move, because blood is an object, unless something pushes blood. So what this thing which pushes blood, it is the contraction of the left ventricle, which generates pressure, and the contraction of the right ventricle, which generates pressure. And this was actually described by William Harvey. So William Harvey, the discoverer of the circulation, in سنة 1628 stated that movement of the blood is constantly in a circle, اللي هي circulation. البلد بيمشي في السيستميك circulation وفي البلمونري circulation. And this movement is brought about by the beat of the heart. يبقى لازم عندنا الهارت على أساس to push the blood. The heart generates pressure, and it is this pressure which pushes the heart. So the right ventricle provides the energy which is necessary to move blood through the pulmonary circulation. And this energy is very important to overcome the resistance. Without this energy, blood will not move. Similarly, the left ventricle provides the energy which is necessary to move blood through the systemic circulation. This energy is in the form of pressure. Thus, the left and the right ventricles are not only flow generators, but they are also pressure generators. So, pressure generation by the left ventricle and by the right ventricle is necessary to counterbalance the energy loss in the vasculature because of the resistance to the flow. Because now the left ventricle ejects blood into the aorta with pressure. Now as blood flows through the aorta and its branches, this pressure, this energy, because of the resistance to the flow, the pressure decreases. And by the time blood reaches the right atrium, it would have very, very low pressure. So now it is the function of the right ventricle to contract during systole and to provide enough energy and enough pressure to push blood into the pulmonary circulation to overcome the resistance of the pulmonary circulation. So then a very important function of the pressure generation is to counterbalance, يعوض the energy lost in the vasculature because of the resistance to the flow. Another important function of the pressure generation is to keep the arterial pressure higher than the venous pressure. So now the left ventricle keeps on ejecting blood with pressure during systole. So the pressure would be high into the aorta. And remember, the pressure is low here because of the previous circulation. So blood would continue to move from the aorta in the direction of the right atrium, because pressure is high into the aorta, is much higher in the aorta than the pressure in the right atrium. Similarly, pressure is much higher in the pulmonary trunk than in the left atrium. And it is because of this pressure difference that blood flows through the systemic circulation and through the pulmonary circulation. Now, a very important question to you. Do the left and the right ventricle generate equal pressures? The answer is definitely not. We mentioned that the left and right ventricle generate pressure to overcome the resistance. And since the resistance in the systemic circulation is 6 times higher than the resistance in the pulmonary circulation, then it is obvious that the pressure generated by the left ventricle is 6 times higher than the pressure generated by the right ventricle. And this is what we have here, guys. So this diagram summarizes the components of the systemic circulation. So we have the left ventricle, then we have the aorta, we have the arteries, we have the arterioles, we have the capillaries, we have venules, veins, then blood ends into the right atrium. So on the left axis, on the x-axis, we have the components of the systemic circulation. On the y-axis, we have the pressure. So inside the left ventricle, when the left ventricle is in diastole, it is in relaxation and is filled with blood. It doesn't generate pressure during diastole. In fact, the pressure in the left ventricle during diastole is 0. 0, it means atmospheric pressure. And this is a long story which will be described to you in respiratory physiology. What's meant by 0 pressure. Then when the left ventricle contracts during systole, the contraction of the left ventricle during systole is to do 2 things: to generate flow and to generate pressure. Look at this. The pressure now increases and it reaches a maximum level of 120 millimeters of mercury during systole. Then when the left ventricle is in diastole, the pressure decreases because now it is in relaxation. Again, now the left ventricle is in systole. The pressure increases from 0 to 120. Then this is during diastole. It decreases from 120 to 0. So this is what we have inside the left ventricle. What we have inside the arteries, inside the aorta, and inside the medium-sized arteries. Inside the aorta, during diastole, when the left ventricle is in diastole, there is no ejection of the blood into the aorta. But the pressure in the aorta is not 0 because the aorta doesn't relax. The pressure in the aorta during diastole, while the left ventricle is in diastole, is 80 millimeters of mercury. Then when the left ventricle is in systole and it ejects more blood into the aorta, it ejects the stroke volume, this increases the pressure into the aorta. So now the pressure in the aorta increases from 80 to 120. And when the left ventricle stops systole and begins diastole, blood flows from the aorta to the tissues. So the pressure decreases from 120 to 80. Same thing in systole, it increases from 80 to 120. Then during diastole, it decreases in the aorta to 120 to 80. So this is what we have in the arteries. So if we take the mean pressure in the arteries, mean pressure and pressure during systole with diastole together, it is about 90 or 93 millimeters of mercury. Now, as blood goes شايفين what happens in the arterioles. The arterioles, the pressure decreases. The pressure decreases in the arterioles because the arterioles are the site where we have the maximum resistance in the circulation. لأن هي البوابات، هي الباب، والباب ممكن يتقفل, and if the door closes then the resistance increases. As blood flows through the capillaries, still the pressure decreases. And as blood flows through the venules and the veins, still the pressure decreases. And by the time blood reaches the right atrium, the pressure is almost zero. So there is pressure drop in the systemic circulation. Now it is the function of the right ventricle to begin the pulmonary circulation. And here we have what we have in the right ventricle and the pulmonary circulation. Now in the right ventricle, pressure is zero during diastole because again it is in relaxation. Then the right ventricle begins systole and generates flow of blood, which is exactly equivalent to the flow generated by the left ventricle. But look at this, the pressure which is generated by the right ventricle, the maximum pressure is only 25 during systole. أقل 6 مرات من the pressure generated by the left ventricle, because again the resistance in the pulmonary circulation is much lower, is 6 times lower than the pressure, than the resistance in the systemic circulation. This is what we have in diastole. The right ventricular pressure decreases from 25 to 0. Same thing in systole, it increases back to 25 then in diastole. In the pulmonary artery, the minimum pressure during diastole is 10. And the maximum pressure is 25. Again, this pressure is 6 times lower than the pressure into the aorta. As blood flows through the pulmonary arteries, pulmonary arterioles, capillaries, the pressure decreases. The venules, and by the time blood reaches the left atrium, pressure is very low. So now it is the function of the left ventricle to generate much higher pressure to eject blood into the systemic circulation and overcome the resistance in the systemic circulation. So this table summarizes the pressures in the systemic and pulmonary circulations. Here, these are the pressures in the pulmonary circulation, and here we have the pressures in the systemic circulation. Let's consider the systemic circulation first. So in the left ventricle, the pressure is 120 by 0, and 120 during systole, 0 during diastole. لأن الليفت ventricle بيكون relaxed, بيتعبى بالدم. In the aorta, the pressure, the minimum pressure during diastole is 80, والpressure بيرتفع ل 120 when the left ventricle is in systole and ejects stroke volume into the aorta. المين pressure اللي هو أثناء السيستول والديستول قلت لكم 90 أو 93. طيب البريشر ده الدم ماشي في الارتريز وصل للكابيلاريز بيقل البريشر في السكيليتال ماسل كابيلاريز تقريبا البريشر 30، يبقى البريشر نقص من 90 بقى 30. وصل للفينز بقى 7 و15. وصل للرايت اتريوم بقى 0، ففي بريشر دروب. This is what we have seen in this figure. This is the pressure drop in the systemic circulation. So now there is a pressure gradient. Pressure gradient هو فرق البريشر between الأورطة and between الرايت اتريوم. قلنا المين بريشر في الأورطة 93 والبريشر في الرايت اتريوم 0، يبقى فرق البريشر بين الأورطة وبين الرايت اتريوم 93 ناقص 0 يعني 93 ملم في ميركوري، وده اللي هو بيخلي الدم يندفع ويفضل ماشي من الأورطة عبر التيشوز في اتجاه الرايت اتريوم. This is what we have in the pulmonary circulation, which we have described here. So the pressure in the right ventricle 25 by 0 أثناء الدايستول when the right ventricle is in relaxation and filled with blood. It doesn't generate pressure. Pressure is 0. When the right ventricle contracts and in systole, it generates only 25 millimeters of mercury. In the pulmonary artery, the pressure is in diastole المينيمم 10 والماكسيمم 25. يعني تقريبا سدس البريشر for the aorta، والمين بريشر 15. remember هنا المين بريشر 93 وهنا المين بريشر 15. as blood flows البريشر بينقص في البلمونري كابيلاريز 7 ل 9، البلمونري فينز 5، يصل للليفت اتريوم منخفض جدا تقريبا من 5 ل 10. يبقى في برضه بريشر جريدينت في البلمونري سيركيوليشن. البريشر في البلمونري ارتري المين بريشر 15 وفي الليفت اتريوم 5، يبقى فرق البريشر 10، وفرق البريشر ده هو اللي بيمشي الدم في البلمونري سيركيوليشن. This pressure gradient is what makes blood flow through the systemic circulation. Now we have finished almost with why do we need to have the heart as the central pump of the cardiovascular system. It's to generate two things, flow and pressure. Pressure to overcome the resistance. So now questions for you guys, and I will not answer these questions. I will leave these questions for you to answer during the class time. Compare and contrast the anatomy of the left ventricle and the right ventricle. Now they are different. The anatomy of the left ventricle is different from the anatomy of the right ventricle. The left ventricle, the wall is 3 times as thick as the right ventricle. Why? Because the left ventricle should be much stronger than the right ventricle, because it should generate 6 times the pressure generated by the right ventricle. The shape of the left ventricle is like a cylindrical in shape and circular in cross section. And this is the shape which is optimal for the generation of high pressure. Whereas the right ventricle, look at its shape. It is crescent shape, شكله هلالي. Why? Because this is the optimal shape of the right ventricle to generate equal flow, which is generated by the left ventricle but with low pressure. الاكتيفيتي قلناها، البريشر جنريشن، الفوليوم. طبعا الفوليوم بتاع الليفت فنتريكل والفوليوم بتاع الرايت فنتريكل از ذا سيم. فلو جنريشن، الفلو بتاع الليفت فنتريكل هو نفس الفلو، يبقى 5 لتر بيندفعوا من الليفت فنتريكل كل دقيقه اللي بنسميها الكاردياك اوتبوت، و5 لتر بيندفعوا من الرايت فنتريكل كل دقيقه واللي بنسميها الكاردياك اوتبوت هنا. ولكن ال5 لتر بيندفعوا from left ventricle with high pressure, and these 5 liters are ejected from the right ventricle with low pressure, because these 5 liters they go through the lungs only, whereas these 5 liters, the left ventricular cardiac output, they go through all systems of the body. So it is a long journey. Now we have finished with the function of the heart as the central pump of the cardiovascular system, and let's very briefly describe the organization in the circulatory system. And we mentioned this. We mentioned earlier in the lecture that the two main circulation, remember this is one circulation, begins with the left ventricle. شايف it goes to the systems of the body, then the oxygenated blood returns to the right atrium. So this is the systemic circulation. Then the pulmonary circulation begins with the right ventricle. Blood goes through the lung. We have entire circulation for left atrium. So this is the pulmonary circulation. These two circulation are arranged in series على التوالي. One circulation ends, the other circulation begins. Now let's focus on the systemic circulation only. الدم اللي رايح ل all systems of the body. How the vasculature is arranged. In the systemic circulation itself, the blood vessels are arranged in parallel. لأن ده الدم رايح for example للliver. This goes to the kidneys. This goes to the skin. This goes to the skeletal muscle. Same thing we have here. So the systemic and the pulmonary circulations are in series with each other, whereas the systemic capillary beds are in parallel with each other. So this is the systemic. For example, this blood, it goes to the abdomen. This goes to the muscle, goes to the kidney, skin, others. So these are arranged in parallel. The kidney and the liver and the gut, they are exception, and we will describe this exception in details later on. Let's now very briefly describe the significance of this parallel arrangement of the capillary beds into the systemic circulation. Why are these capillary beds are arranged in parallel in the systemic circulation? There are reasons for this. في حكمة Allah subhanahu wa ta'ala خالق this parallel arrangement of the capillary beds in the systemic circulation. This is to make sure that all tissues receive oxygenated blood at the same time. Had these organs of the systemic circulation, had they been arranged in series, this would mean that the first organ would receive oxygenated blood, then the subsequent organs would receive less and less and less oxygenated blood. So this is one reason, to make sure that all organs would receive oxygenated blood. Another thing is to make sure that these organs do not receive equivalent amount of blood. Now, the blood which flows through the different organs of the systems of the body depends on the activity. If the tissue is active or the organ is active, البوابة بتاعته هتكون مفتوحة and it receives more blood. If it is less active, for example the skin, شايفين السكين هنا؟ البلاد فيزل بتاعته ضيقة أكتر من الskeletal muscles, because less blood goes to the skin, because the skin is not as metabolically active as the muscle. The kidneys, they receive larger volume of blood because the kidneys, as will be described to you in one complete course, the renal physiology, their function is to filter the blood. So they should receive high volume of blood in the systemic circulation. So now, the arterioles here, they determine how much blood flows through the different organs of the body. So it is the resistance of the arterioles which determine how much blood flows to the different organs of the body. So the parallel arrangement of the capillary beds, this enables redistribution, إعادة التوزيع of the blood flow between the various capillary beds as it occurs when the metabolic rate changes differently in the various tissues. لما الواحد السكيليتال ماسل فيها ميتابوليزم كتير during exercise تتفتح الارتريولز بتاعت السكيليتال ماسلز وتتقفل الارتريولز بتاعت السكين for example. So thus the arteriolar diameter determines the arteriolar resistance, and the arteriolar resistance determines the perfusion الانسيابية بتاعت الدم through an organ. This is again one of the important reasons why in the systemic circulation the organs, the capillary beds are arranged in parallel. Had they been arranged in series, this wouldn't be the case. Finally, in this lecture, we should know that each tissue should receive only a fraction of the total cardiac output. It doesn't receive all the cardiac output because the tissues in the systemic circulation are arranged in parallel. بياخد جزء فقط. Each tissue must receive only sufficient blood flow for its metabolic needs. It shouldn't receive less blood because if it receives less blood, the tissue will die and will undergo necrosis. And the tissue should not receive more amount of blood than it requires. لأن لو التيشو أخذ كمية كبيرة من الدم معناها القلب لازم يضخ كمية أكبر من الدم، معناها في عبء على القلب. So each tissue then should receive only sufficient blood flow for its metabolic needs. So by controlling a tissue perfusion to each tissue, this would mean that each tissue receives just enough blood. وبالتالي الكاردياك output would be enough for all tissues and the work of the heart is minimized. القلب يشتغل بالحد الأدنى. مش عايزين نرهق القلب ويشتغل بالحد الأدنى. So this is what we have here. So for example 4 لتر، طبعا احنا قلنا 5 لتر اللي بيروح للتيشوز at rest. here we have الارتريولز، دي البوابات اهي رايحه للتيشوز. So in this scenario the total perfusion 4 لتر رايحين for example ل 4 tissues. for example لو اعتبرنا ان في الجسم فقط في 4 organs او 4 tissues، يبقى هنا لان البوابات دي مفتوحه بنفس المقدار معناها ال4 لتر هيتوزعوا بالتساوي، 1 لتر بالدقيقه، 1 لتر بالدقيقه، 1 لتر بالدقيقه، 1 لتر بالدقيقه، بعدين يتجمعوا ال4 لتر. However this is not the case in the body because the tissues they have different metabolic needs and metabolic requirements. Now look at this. This organ receives 2.5 liters per minute. Why? Because it has higher metabolic requirement. وبالتالي الباب بتاعه مفتوح فالريزيستنس أقل. بينما these now they have less metabolism so they receive less blood. That's why من حكم الله عز وجل أن جعل الكابيلاري beds in the systemic circulation arranged in parallel. And this what we have, guys, how the cardiac output, how the resting cardiac output is distributed at rest and during exercise. So at rest the cardiac output from the left ventricle is 5 liters per minute. Of these 5 liters 13 ل 15% بيروح للبرين، 4 ل 5% يروح للهارت، 20 ل 25% بيروح للليفر والجت، وبرضه 20 ل 25% بيروح للكدنيز، much less بيروح للسكين، and برضه قليل بيروح للفات والسكيلتون، كمية كبيرة يعني relatively كبيرة بتروح للسكيلتال muscle. Again this depends on the metabolic activity of the tissue. And again what determines how much blood؟ الباب، الارتيريول مفتوح ولا مقفول؟ ومين اللي بيحدد الارتيريول مفتوح ولا مقفول؟ الميتابوليك activity of the tissue. During exercise the cardiac output increases to 25 liters per minute and it might even increase to 35 liters per minute in well-trained athletes في الأشخاص الرياضيين. Now this is what we have here. Now most of these 80 to 85% of these 25 liters would go to the skeletal muscles during exercise because now the skeletal muscles they require much more oxygen and much more nutrients during exercise. فتبقى الارتريولز البوابات بتاعت الكابيلارز اللي موجوده في السكيلتال muscles مفتوحه على مصراعيها so that the skeletal muscles would receive large volume of blood and large contribution or percentage from the cardiac output. And that's the end of these 2 lectures. Here we have again the learning outcomes which we will go through again during the class time, and thanks very much for listening. So I would recommend you guys to go through the learning resources and to listen to the video before coming to the class time because I will adopt the flipped classroom model in my lectures, and because of that I will provide you with the videos before the class time, and thanks very much.